Oh, sorry. I said good evening, Shastri Garu. Thanks for
Our director, sir, is there, sir? Professor Pramod Padale.
Namaskar, sir.
Namaskar.
Sir, he is Professor Dr. H.N. Das, sir, Scientist G in NSCL, Naval Science and Technological Laboratories. I will, sir, with your permission, if you say I wish to start the FDP, sir.
Yeah, you can start.
Sir, respected Honorable Director, sir, Professor Pramod M. Padale, sir. Sir, our Dr. H.N. Das, sir, Scientist G in NSCL, Naval Science and Technological Laboratories. I will, sir, with your permission, if you say I wish to start the FDP, sir.
Yeah, you can start.
Sir, respected Honorable Directors.
Sir, not audible, sir. Sir, not audible.
Welcome our Honorable Director, Professor Pramod M. Padale, sir, and our chief guest of the function, Dr. H.N. Das, Scientist G, and my co-coordinator, Dr. Santosh Kumar, Registrar in charge, Dr. Dinesh Sankar Reddy, HOD Dr. Babu Rao, my dear all participants, good evening to all. So today, with the great support of our director, sir, we started Department of Mechanical Engineering, started a 2-week online FDP on condition monitoring hydrodynamic design of marine vehicles. It will be from 9th November to 20th November. And the first week will be online from evening 7 o'clock to 9:30. And the second week will be offline. And in this regard, now I request our registrar, Honorable Registrar Dinesh Sankar Reddy, to give the overview of NIT Andhra Pradesh. Thank you, sir.
Thank you, Professor Sastry, sir. Respected Director, NIT Andhra Pradesh, Professor P.M. Padale. Today's chief guest, Dr. H.N. Das from NSTL. Coordinators of this FDP, Professor G.R.K. Sastry, sir. Co-coordinator of this FDP, Dr. Santosh Kumar. Head of the Department Mechanical Engineering, Dr. Babu Rao. Other faculty members of Mechanical Engineering. The participants have joined, are registered for this 2-week-long FDP program. A very good evening to all of you. At the outset, I welcome you all for this 2-week-long FDP program sponsored by Atal Academy. And in fact, once this Atal Academy has started a 2-week FDP programs as an extension to 1-week FDPs, this is the first of such program being awarded to NIT Andhra Pradesh. And in fact, I congratulate Professor G.R.K. Sastry, sir, as well as Dr. Santosh for getting this Atal FDP. And as well, you would have observed, even the Atal Academy has changed minor changes, and in order to accommodate all the faculty who will be registering to attend all the sessions, they have made this FDP program to start every day at 7 p.m. in the evening, so that everyone can join. And at the same time, it has solved many problems for the organizers, wherein they can invite eminent faculty without compromising on their regular schedule. Minor changes, and in order to accommodate. Very briefly, I'll go through the journey of NIT Andhra Pradesh. This is the youngest NIT among the 31 NITs started by Government of India. It was established in the year 2015, and we are now 7 years old. Though it is an youngest NIT, but we have established the facilities quite rapidly. In fact, in a record span of time, we have started functioning from our permanent campus from the year 2019 December, and we have all the required amenities for the sake of students, be it hostels, as well as good number of laboratory space, nearly 40 laboratories we can accommodate, two academic complexes, administrative blocks, indoor auditorium, cafeterias. So everything which is required for all the stakeholders of the institute are all in place at NIT Andhra Pradesh. Of course, the number of faculty wise, we are very small still. We are only 44 on roll, though the number is less, but the contributions made by these faculty members are enormous. During the last 2 to 3 years, the faculty members were successful in getting nearly 26 sponsored research projects worth of 5.4 million rupees. Also, we have made MOUs with nearly some 24 to 25 organizations, as well as the faculty have filed 18 patents till date. Uh, 1 year before, with the support of Department of Electrical Engineering, the institute has got one research technology hub in the domain of renewable energy with a funding of 7.15 crores, wherein 5 crores was sponsored by Department of Scientific and Industrial Research. For an young institution, this is a remarkable achievement. As well, now projects worth of 2 to 3 crores are in pipeline. Very soon, we are expecting the orders will be coming. And during the pandemic, as well as a continuing of this imparting the knowledge acquired by our faculty as well as the eminent faculty to the nearby private colleges as well as the colleges in and around our place. So institute is organizing many FDPs, and it's a good sign that Atal Academy is also sponsoring a good number of FDPs under this. Also, finally, to end, the institute has carved its name in terms of providing placements to its students. Almost for all the 4 passed out batch students, we have provided 90 to 100% of the placements with an annual CPC of 8.5 lakhs, and the highest package secured by our students is around 48 lakhs. And for the next 3 to 5 years, the institute is focusing to have few state-of-the-art research laboratories as well as few centers of excellences. I hope with the support of Minister of Education and the staff and the director, so we could able to succeed and will move on the right path. I once again congratulate the coordinators for acquiring this particular program, as well as on behalf of NIT Andhra Pradesh, I thank all the speakers who have given their consent to be a part of this FDP program. Thank you.
Thank you very much, sir. Thank you, Honorable Registrar in Charge, Dr. Dinesh Sankar Reddy, for nicely elaborating the overview of NIT Andhra Pradesh. Before requesting our Honorable Director, sir, now I request my PhD scholar Narasimha to introduce our Director, Dr. Pramod M. Padale, because all the 50 participants are from the outside. So Narasimha will introduce our Honorable Director, sir. Thank you.
Good evening, one and all. It gives me an immense pleasure to introduce our president of the today's program, Professor Pramod M. Padale, sir, Director in Charge, NIT Andhra Pradesh, Director VNIT Nagpur. Professor Padale, sir, is an erudite professor, popular teacher, and eminent researcher with a dream to use science and technology for better community life. He did his BE in Mechanical Engineering and PhD from VNIT and Masters in Machine Design from VJTI Bombay. His researchers include mechanisms and machine design, finite element method, and biomechanical engineering. Professor Pramod sir has guided 17 PhD research scholars and supervised more than 50 MTech projects. Presently, 4 PhD research scholars are working under him. He has more than 140 research publications in reputed international and national journals to his credit. He has 2 patents to his name. Professor Padale sir also worked as the president of Biomedical Engineering Forum and developed functional and applied technologies and implants. Professor sir has successfully completed more than 14 consultancy projects in the areas of appropriate technology, design and finite element analysis, which were funded by DST, Ministry of Education, KVIC and AICT. Professor Padale sir has received Academician Par Excellence Award from Institution of Engineers in 2017 for his lifetime contribution in the areas of product development, process development, and technology transfer. He has also received Best Science and Technology Innovation Award from Government of India from KVIC sponsored project and developed 10 intervention technologies for creating self-sustainability and economic development of rural sector. Now I request Professor Pramod M. Padole sir to deliver the presidential address. Thank you, sir.
Sir,
Thank you,
welcome, sir.
Narasimha. Thank you and very good evening to all of you. The chief guest of this today's inauguration function, Dr. Das from NSTL, the scientist G, the coordinator of this Atal Academy FDP program, Professor Shastri, co-coordinator, Professor Santosh Kumar, the registrar of the institute, Dinesh Shankar Reddy, all the faculty members of the mechanical engineering department particularly, and the faculty members of the other departments also, and the participants for this 2 weeks FDP program under Atal Academy, which is in the area of the condition monitoring and hydrodynamic design of the marine vehicles. Right? This, I think, is a very relevant sort of area which has been selected by the coordinator, because all of us are aware that condition monitoring plays a very important role in any of the system. Particularly, this is for improving the reliability of a system, then to improve its residual life assessment, and all those kind of things. And I've been told that there are the experts in this area who will be sharing their views during this FDP program, and all the faculty members and the researchers will be getting a sort of advantage to listen to these experts and learning more in the area of the condition monitoring and the related areas. There are experts from this naval science and technological laboratories. Then there are experts from various IITs and NITs who will be delivering their lectures during this uh, 2 weeks. As I've been told that the first week is online and then the next week will be in a physical mode. In fact, I am very happy that this NIT is quite young. As I've been told that these are one of the youngest sort of the NITs. But if I see when I'm looking and discussing with the faculty members, the progress that they have done is really remarkable. The many of the laboratories have been set up. They are getting the consultancy and the R&D projects from various organizations. As I've been told by the registrar that recently the electrical engineering department had got a project which is costing about 7 crores, and 5 crores have been funded by the ministry and other agencies. So the progress is quite satisfactory. And when I have been interacting with the various faculty members, including Professor Shastri and others, I found they are very dedicated, very sincere, and they have got a desire to do something for this very, you can say, the new institutions, because it is only the contribution and the sincere efforts by the faculty members and the researchers and the students, who are all stakeholders, the institute can reach to the new heights. In this regard, the organizing such kind of the programs, faculty development programs, the conferences, the workshops, and this thing, that will definitely uh, bring all the faculty members and researchers together, and they will be putting their hands together to see that they are reaching to the new goals, and they are getting some new milestones. They can set that. So these are good things. I am very happy that I have been invited over here uh, to for this inauguration of this FDP program. And this area, of course, that is wide open area. The condition monitoring is very much required, not only for the mechanical system but for various systems. And this condition monitoring is a very useful sort of a area, and that definitely see to it that your systems are working nicely. They are always on, so that you can ensure, and also you can predict the reliability and the life of the whole system. So once again, in fact, as an in charge director of this NIT AP, I welcome all the faculty members and the participants for this FDP program. I am sure that this 2 days, 2 week program will be very useful, fruitful, and meaningful, and the all the participants will be. I can say that it will be feast, academic feast for all of them, and they will be uh, encouraged sort of thing to carry out their research in this area, and they'll be gaining knowledge from the various experts who will be delivering their or sharing, I will say, the experiences in the area of the condition monitoring. With this, once again, I welcome you all, and thanks the organizer for inviting me over here to share my views. Thank you very much. Thank you, Professor Shastri.
Thank you very much, sir. It is indeed our pleasure. You are the president of the function today, and not only you are always president to us. And thank you very much, sir. And I request HOD Mechanical Engineering to give the overview of the department.
Yeah, thank you, sir. Respected dignitaries, dear colleagues, and participants, very good evening. I take this opportunity to present the overview of Mechanical Engineering Department, National Institute of Technology, Andhra Pradesh. The department offers BTech undergraduate program in Mechanical Engineering, 2 MTech programs such as Manufacturing Engineering and Thermal Engineering, MS by Research, and PhD full-time and part-time programs. The Department of Mechanical Engineering was incepted in the year 2015 with a sanctioned intake of 60 students for the BTech, and now it has enhanced to 120 students. The sanctioned intake of 15 students for each MTech program for the academic year 2020-21 onwards. The curriculum offered for BTech program includes core courses providing a comprehensive theoretical foundation, which is supplemented through industry relevant elective courses and a project component. The MTech curriculum is designed in such a way to enrich the theoretical and practical foundation for the conduction of high quality research in the respective domains. The faculty members in the department works on research domains such as design engineering, manufacturing engineering, thermal engineering, and materials engineering, to name a few. The department has organized so far 5 faculty development programs. Faculty has been publishing impact publications in reputed national and international journals as well as conferences. As of now, the Faculty of Mechanical Engineering Department has published 8 patents, and the department is equipped with state-of-the-art laboratories for conduction of UG program. And the department is currently in the process of establishing laboratory facilities with state-of-the-art research equipment. And I congratulate the coordinators for organizing this event to enlighten the participants in the area of condition monitoring and hydrodynamic design of marine vehicles. Thank you very much.
Thank you, Dr. T. Baburao, HOD Mechanical Engineering. Sir, actually, just we are differing the schedule, and I request Sairam to introduce the chief guest of the function, as the director sir is here. Then Dr. Das sir will say few words, his blessings to the this, then followed by vote of thanks. Dr. Sairam, please.
Good evening to one and all. It is a great honor to introduce Dr. H.N. Das, chief guest of today's program. Dr. H.N. Das is currently working as a scientist G at Naval Science and Technological Laboratory, Visakhapatnam. He completed his BE and ME from Jadavpur University, Kolkata, and PhD from IIT Delhi. Currently, he is the project director for
high endurance autonomous underwater vehicles in NSTL Visakhapatnam. During his service, during his 25 years of service, he worked in several positions like scientist in hydrodynamic wing for structural design and model testing of underwater missiles, staff officer for maintaining all civil structures, project leader for hydrodynamic performance evaluation, head of CFD division. His area of research includes shape optimization of underwater vehicles, vehicle dynamics and their trajectory, multi-phase flow for cavitation studies, maneuverability and stability of underwater vehicles through hydrodynamic coefficients, advanced hull form design for high-speed ships. He is the recipient of many medals like H.S. Rao Memorial Award, DRDO Silicon Medal, Swapan Chandra Memorial Medal, etc. He has more than 50 research papers to his credit, published in national, international journals and conferences. He also guided 15 students for MTech projects. He also worked as a guest faculty for the Indian Maritime University, Visakhapatnam. He has associated with many professional bodies like Journal of Engineering Applications of Computational Fluid Dynamics, American Society of Naval Engineers Publications, Institute of Naval Architects, India. Thank you, sir.
Thank you, Sairam. Now I request Honorable Dr. H.N. Das Gar to say a few words about this workshop. Thank you, sir.
Thanks for giving a nice introduction to me. Respected Professor Himanshu Padole, Professor G.R.K. Shastri, Dr. Santosh Kumar, all the professors and faculty and participants present here. It is indeed a privilege for me to get associated with NIT Andhra Pradesh. As the description of this institute has already been given, it has a short journey, but within the short time it has achieved a lot. And it is my privilege to get associated with Professor Padole sir and this organization. And I congratulate the organizers to choose such a subject and conduct a FDP. And I am very thrilled that a mechanical engineering department is conducting a course on hydrodynamic design of marine vehicles as well as condition monitoring. And that is the need of the hour. Because in engineering now it is becoming multidisciplinary, and we engineers have come and progressed in such a way that all the disciplines we have to do together, and that way we are ahead of medical science people. I see that medical science people, they go for super specialization. Their department is like ENT department says it is my ENT is my subject and not the kidney, not the heart. But the person is one. They lose the focus to see it in totality. Whereas we engineers actually see it in totality, and that's why our system engineering has come, and your course is a proof of that. So you have understood you have understood the requirement and the need for this, and design of marine systems, hydrodynamic design marine systems, as well as condition monitoring together, and that is organized in mechanical engineering department. I put hats off to you for choosing such a subject, and I wish all the best for the course. You will be running in offline mode and online mode for 2 weeks, I understand. So I wish my best wishes for all the success of the course. Thank you very much.
Thank you, Das sir. I request my co-coordinator, Dr. Santosh Kumar, to say vote of thanks, so that then followed by the session starts. Thank you, Dr. Santosh.
Thank you, Professor G.R.K. Shastri, sir. Good evening to one and all present here. Respected Director in charge, Professor M. Padole, sir, in charge Registrar and Dean Faculty Welfare, Dr. Dinesh P. Shankar Reddy, sir, our Chief Guest, Dr. H.N. Das, Scientist G, NSTL Visakhapatnam, Dr. T. Babu Rao, Head of the Department Mechanical Engineering, Deans, Associate Deans, Head of various departments, faculty, staff, UG, PG and PhD students, and other invitees. It's indeed a great pleasure to propose the vote of thanks. I take this opportunity to thank our beloved Director in charge, Professor Pramod M. Padole, for decorating this program with his presence and addressing all of us in his presidential address. And Sir also spoke about the importance of condition monitoring and its applications in the relevant areas. We thank you, Sir. And indeed, great pleasure to thank our chief guest, Dr. H.N. Das, Scientist G, NSTL Vishakhapatnam, for gracing this function and delivering the inaugural lecture. I also thank our in charge registrar and Dean Faculty Welfare, Dr. Dinesh P. Shankar Reddy, sir, for his support, presence, and for delivering the welcome address and giving the overall view of NIT Andhra Pradesh. Sir, we thank you. And also, I thank our head of the department, Mechanical Engineering, for giving the overall view and the courses offered by the Mechanical Engineering Department. I thank web and networking team for their efforts in maintaining the network connectivity. And also, I thank Mr. P. Narsimha Shivateja and Mr. Sairam for being an outstanding master of ceremony. Finally, I thank all the people who are directly and indirectly helped in organizing this particular workshop. Thank you, sir.
Thank you, Dr. Santosh. Sir, thank you, sir. Padala, sir. And we request you to come for the offline also if possible. Thank you very much, sir.
I am very happy that you are organizing this, right? And I wish you all the best.
Sir.
Let us conduct few more such courses.
Sir.
I am with you, right?
Thank you, sir. Namaste, sir. Namaste.
Thank you, sir. Thanks a lot, sir.
Right.
Thank you, sir. And also our thanks goes to all the deans, HODs, and faculties also who joined. And sir, now the session will start. I request Das sir to give his session. Thank you, sir.
Yeah, thanks for giving this opportunity. I will share my presentation and
Sir.
I will start my talk. Just give me 1 minute to share the
Yes, sir.
presentation.
Yes, sir. Take your own time.
Just give me 1 minute to share the presentation.
Thank you.
Yeah, is my screen visible to all of you?
Yes, sir. It is visible, sir.
Okay, I just checked. This is moving. No, screen is moving. My
Yes,
slides
sir.
is moving.
Yes, sir. Yes, sir.
Yeah, yeah.
Yes, sir. It is moving, sir. Thank you.
So thanks. We will start the session. We will start with the subject, an overview of computational fluid dynamics. So this course starts for conditioning monitoring and hydrodynamic design for marine vehicles. So computational fluid dynamics will fit as a part of, as a tool to do hydrodynamic design for marine vehicles. So though it is an inaugural lecture, I will concentrate on computational fluid dynamics only. But best part is that computational fluid dynamics is not only applicable to design of marine vehicles, it is applicable to so many other fields. Almost every field it is used. So that way, it may be appropriate to start the session with lecture on computational fluid dynamics. So I assume all of you are familiar with fluid dynamics. Quickly, a confirmation. Can I get a confirmation quickly that you are all familiar with fluid dynamics? And from there, I will just give a introduction on computational fluid dynamics. And if you people are already familiar with computational fluid dynamics, that also you can just quickly, can you give me a confirmation?
Sir, can you hear
in
me?
this message box I can see, or if there is no other issue, I assume that you know fluid dynamics, and computational fluid dynamics is something we will get introduced now. It's okay, then I start.
Yes,
Yeah.
sir. Please proceed.
Yeah. See, this I first describe what is the fluid flow problem. What we talk about fluid dynamics. When we say fluid dynamics, actually science deals with some measurable parameters. So when we talk about fluid dynamics, there are primarily these are the parameters, these are the variables which we are interested of. So if there is a fluid flow, that fluid flow can be anywhere. It can be a flow through a pipe. It can be flow around an aircraft. When the aircraft moves through air, it receives the relative flow. When a ship moves or a submarine moves through water, in all the cases, wherever, if there is a fuel injection inside a vehicle engine, when the fluid moves, primarily we want to know what is the pressure, what are the velocities at different places, velocity components, what is the density, what is the temperature, and is there any scalar. The scalar means, see, if there are two different type of fluid, a mixture of two fluids, then what is the concentration of this mixture? That is a scalar. Similarly, there may be many scalars. So primarily in the fluid flow problem, these are the parameters we need to know. And if we can know in a flow domain all the parameters, we say that we know the fluid. So that's what we want to know. In fluid dynamics, basically, we want to know these parameters. Now, what are the ways to do or to know these parameters? I'll say there are three approaches. Okay, one is analytical fluid dynamics. That is the classical approach, which is existing for since long, and it started, in fact, long back from the Archimedes time. It is more than 2,000 years old. Classically, we try to write the fluid flow equations. That's one approach. We call it theoretical fluid dynamics. And it really picked up sometimes like 1600 AD or so, when all the fluid dynamics, in Europe basically, this research went on, and fluid dynamics, all the theories, equations were written. That is the classical or theoretical fluid dynamics approach. Unfortunately, fluid dynamics equations are very complex and not yet solved today. I'll come to this issue. So that's why with theoretical fluid dynamics, we have advanced with the theory, but we don't have a complete solution in theoretical fluid dynamics. That is the limitation of theoretical fluid dynamics. Theories are available, but we don't have the solution. Then second approach is that experimental fluid dynamics. That another approach is that, say there is a pipe flow, and I don't do any theory. I just put some probe inside the pipe, and that probe will measure the velocities, the pressure, etc., etc. So at different location, I get all the parameters through my experimental measurement. That is experimental fluid dynamics. This is also say around 300, 400 years old. Started from, say, Leonardo da Vinci has tried to do the first model testing, and that is the time, that is in 1600, even 500 years old. But it really picked up like last 200-300 years, that all experimental techniques, and we established many experimental techniques to find out the fluid flow problems. So these are quite established, quite old. There is one more one more approach, that is CFD or computational fluid dynamics, which is emerging, which is, I will say, around 100 years old. It is not more than 100 years old, and not even 100 years old. It is very emerging technique. It says that if the theoretical equations cannot be solved as it is, we use some computational or numerical approach to solve this equation. So this numerical approach will give me some approximate solution. To some extent, they are approximate, and we will go ahead with the solution. So this is the computational fluid dynamics, and this is the place where it sits. So as I said, CFD is computationally solving the fluid flow problems. Okay, and see, as I said that it is 100 years old. Okay, CFD formulations are 100 years old, but 100 year back we did not have computers to solve these equations, to numerically solve these equations. So that's why, though some of the equations were available, some of the techniques were available, we did not have computers to really solve them. And that computers actually started coming in 1950s or 60s or so. So that way, you can say CFD is only 70 years old. It's a relatively new, it's very new technique. And see the advances. We had a 500 flop machine in 1947, that is the maximum. Now, in 2022, we have exaflop machine, 1.1 exaflop or 1100 petaflop machine. So the power, computational power has increased enormously. And because computational power has become available, it has become cheaper, CFD has gained popularity. So to becoming popular, computational facility, advances of computational facility played a huge role making CFD popular. And where CFD is used, in the beginning itself, I said that CFD is multidisciplinary. In so many fields it is used, and that's why it may be very appropriate to start the session with a lecture on computational fluid dynamics. So I have shown some of the fields here. There are many, starting from aerospace engineering, automobile engineering, chemical reactor. Inside a chemical reactor, the CFD is done to solve fluid flow inside chemical reactors. Even biomedical field, for a laser surgery, for a eye operation, how the fluid will be flown out and will be taken out, like a cataract surgery, how the cataract will be taken out after giving a laser ray and liquefying, after liquidifying this cataract, that extract has to come out, and how that will be coming out is also solved through CFD. And it is used in electronics for a cooling design, how the cooling is designed in a PCB, and in a complicated system where many PCBs are placed, how the cooling is done, but is also studied through CFD. It is used in manufacturing unit, how the coolant will be effectively cooling a drill bit or a machine bit. Is CFD is applicable. CFD is applied in sports, field of sports also. How a swimmer suit has to be designed so that the best performance reduction of drag is possible in hydraulics. A hydraulic structure, how this flow goes on in a dam or downstream of a dam, CFD is used. Atmospheric and ocean science, like in atmospheric science, how the chimney output will go into the atmosphere, CFD is used. And in marine field, that is mostly I work in, that what is the flow around ships and submarines and all, and how this behavior of the vehicle will be in actual sea condition. CFD is used to predict it. So there is a complete gambit of so many engineering fields where CFD can be used. And I congratulate all of you to sit in this program to see that CFD, what is going on in CFD, which is applicable to so many different fields. A quick answer that why CFD is used. CFD is used because it is more cost effective. I said that now computational power is available with cheap cost. So instead of doing an experiment, which is more expensive and time consuming, CFD is cheaper as well as time effective. Second is CFD provides high fidelity database. That high fidelity database means if I solve a flow domain at every grid point or almost everywhere, I know the answer. I know the pressure, velocities, and everything. Whereas in experiment, I have to first design and put my gauges in some particular places, and in that particular place only I get the result. So, and instrumenting a flow domain is always troublesome. Means you cannot put your gauge everywhere. So that way, CFD gives a high fidelity database, and it can give a full scale simulation like ships and aeroplanes. If you have to do a full scale model test, only very limited one or two wind tunnels are available where a full aircraft can be tested. Ships, it is not possible. There is no such tank where a full ship is tested. Whereas in CFD, we can simulate the full scale thing. And environmental effects and all, like wind and weather effects, CFD is much more effective. Another thing is that hazardous condition. If there are some fluids which are hazardous, which are poisonous, which has a pollution, pollutant, highly pollutant, experiment is dangerous. Whereas in CFD, I just keep the fluid property and still go ahead with the solution. So these are the advantages of CFD. So I think I just want to submit to you that if you have any doubt or any questions, you can pop up and can speak actually in this lecture itself. I have no issue. If you have any doubt, you can ask immediately. As far as development of CFD, as I said, that we started developing the techniques for solving differential equations or solving numerical solution of differential equations since 1910. I will say this is the beginning of CFD. 1910, Richardson has given a famous paper where he has shown iterative solution of Laplace equation. How Laplace equation can be solved. Laplace's equation is a second order partial differential equation, and this partial differential equation can be solved using iterative techniques. So instead of actually solving a partial differential equation, which is normally difficult, in if you excuse me, can I take for a minute? I just receive a call and I'll just come back. Give me. I'm extremely sorry. Yeah. Yeah, so I said that Richardson's paper, where he has given the iterative solution of Laplace's equation, maybe the beginning of CFD, because he has shown the way that partial differential equation can be numerically solved, not exact closed form solution, but numerically solved. And then there are many techniques to solve numerically this partial differential equation. It went on like that. And we all know that CFL condition in CFD, there is a famous condition for explicit solutions, that when the solution can be achieved and when solution cannot be achieved, which is called CFL condition. Courant, Frederick, and Levy, they gave this condition that where explicit solution can be achieved in 1928. So this is the history. I say that this is the time when all these numerical techniques were being developed. And then in later part in 1960 and all, Lax, Wendorf, this is the way to solve the fluid flow equation, partial differential equation involved in fluid mechanics, and offer a numerical solution, Maccormack technique. And then in the later part, we see some of the turbulence models, like turbulent flow, how to model it. In 1972, Cave-Salon model has come into practice. Wilcox gave in 1993, and very recent in 2005, that V2F model has developed in Stanford University. So this is the way the numerical part, the mathematics part got developed. But as I said, in 1910, the techniques were available, but computers were not available. And computers really started coming in, say, around 1950 or so. And there I say that it is initiation of CFD, because people started solving something with CFD. And 1970s, we see that CFD code were handwritten codes, long, mostly done for two dynamic flows, two-dimensional flows, and mostly applied in aerodynamic application. Because aerodynamics is the field which has actually driven CFD. Started from aerodynamics. Whereas another 20 years, 1990, we have seen so many complicated 3D flows can be solved, and commercial code has come like Fluent and CFX and Numeka and all these codes has come in. So they started solving practical problems, actual practical problems, 3D problems, 1990s. And 2000, I see that it was available for the industries. Industry was seeing so many industries, they started using CFD and so many solutions, analysis. In fact, experiment has started reducing after the advance of CFD, say starting from 2000 or so. And 2020, I say that the advances are in multiphysics, many interactions like fluid structure interaction and the interaction like I say in a ship flow that the under water hull is interacting with flow and superstructure is interacting with air. So this air flow as well as water flow and their interaction, they all are modeled now. Like it's from engine, the exhaust gas is coming out, how that is going in the ship deck and how it is interacting with the fluid flow. All these interactions, including fluid structure interaction with many other physics together, which is called multiphysics, is now the trend or things going on in the field of CFD. So with this basic introduction, I'll say, I already said that my objective in computational fluid dynamics is to solve the fluid flow equation to determine the flow characteristics. And these characteristics are pressure, velocity component, density, temperature, and scale. And how do we do it? As I said, there are three approaches. One is theoretical approach, one is experimental approach, and another is computational fluid dynamics, CFD approach. So in theoretical approach, what we say, actually in fluid flow, it describes a transport phenomena. If you see the fluid flow, fluid flows from one place to another place. So it is a transport phenomena. And transport phenomena is governed by some conservation laws, that its properties are conserved. Even if it is transported, its properties are conserved. What are these conservation laws? That our laws from physics says that momentum along a given direction is conserved. Momentum along the three principal direction are conserved. Mass is conserved. Energy is conserved. Even some concentration of different species are involved. These are also conserved. Any other scales, they are conserved. So these are the conservation laws. And for these conservation laws are given by physics. So from physics, I know that mass is conserved, energy is conserved, momentum is conserved. And when we write this equation, when we write these conservation laws, they form the governing equation. And so what I mean that the transport phenomena says that my parameters are conserved in this transport, and this interaction between the transport for these parameters are happening because of convection, diffusion, and source. Convection means one place to another place when it is going, it is carrying some property along with that. Diffusion is that even if the fluid is not physically flowing, but the property is getting transported through the fluid medium. And source is that some property is either generated or getting destroyed. And they are in balance. This all convection, diffusion, and source has to be in balance to give me a conservation. So physics, from this physics, we know that momentum is conserved, mass is conserved, energy is conserved. Energy is conserved. And when we write this, we get the governing equation of fluid dynamics. They are continuity equation, mass is conserved, which gives me continuity equation, Momentum is conserved, gives me Navier-Stokes equation. Energy is conserved, gives me energy equation. So these are the fundamental of fluid dynamics. So when anybody says about fluid dynamics, actually fluid dynamics is based on these three conservation principle. This is mass is conserved, momentum is conserved, and energy is conserved. And there is nothing more other than that. These three are the conservation principle, and on these three conservation principle, we can write three governing equation. They are continuity equation, Navier-Stokes equation, and energy equation. So theoretical fluid dynamics actually develops these equations. As I said, this is around 400-500 years back. These equations are derived and they are available. Not even all these equations, Navier-Stokes equation is only 1800. So you can say 300 years, 200 years old. That is the time when these equations have been written. So theoretical fluid dynamics writes this equation. And how do I solve that? That is the job of mathematician. And mathematicians still could not find a solution for these theoretical equations. That is another aspect. And that's where CFD comes in. Because we don't have a mathematical solution or closed form solution of this differential equation, we need to take some other approaches which are numerical solution or computational solution. And that forms the subject of computational fluid dynamics. So what are these equations looks like? These equations may be scary, but it is actually the fundamental equation of fluid flow. And in many classroom lecture, actually, I derive this equation. And when I derive, you will find that these equations are not that unfamiliar. To get more familiarity with this equation, you have to derive these equations actually on your own hand. If you do that, you will find quite familiar with this equation. However, this is only an introductory lecture. I'll just speak about these equations. I will not go into the derivation and all. I'll just give a description, and that description will be sufficient for today's class. So as I said, that mass conservation gives the continuity equation, and this is the continuity equation. Dou rho dou t plus dou x rho u plus dou y rho v plus dou z rho w equal to 0. This is in non-conservation form, and in conservative form, we write it like that. Dou rho dou t plus div rho v is equal to 0. This is the continuity equation. And for incompressible flow, there is no rho because rho is constant and the equation takes a shape like this. Then the next equation is momentum conservation. Momentum conservation is coming from Newton's second law of motion. And here also it is very simple. It says that mass into acceleration is equal to force. So Navier-Stokes equation actually does not write anything more than that. It writes only that thing, that mass into acceleration is equal to force. So this is the Navier-Stokes equation in three directions, x, y, z. In textbook, you may find Navier-Stokes equation is written in big way and with so many terms and all, which looks scary, but it is not. It says very simple principle that momentum is conserved. That means mass into acceleration is equal to force, because rate of change of momentum is the force. So if momentum has to be conserved, that means equal amount of force has to be used, which is actually second law of motion, Newton's second law of motion. So now just look at this equation. As I said, this is the second law of Newton's motion. Can you identify that? This rho is density, that is mass per unit volume. So for an unit volume, I am writing this equation. Rho is mass per unit volume. So rho is the mass into acceleration. Dou u by dou t is the total derivative. Dou u dou t is total derivative. U is velocity in x direction. So du dt is the acceleration. So mass into acceleration, mass per unit volume into acceleration is equal to all the forces. So what are the forces? dp dou p dou x is the pressure difference in x direction per unit volume, because you multiply by area and divide by the volume. So per unit volume, this is the pressure force in x direction, difference in pressure force in x direction. So this is coming from pressure. Dou tau xx, that is the stress in x direction. Dou tau yx is the shear stress in x direction, and dou tau zx is the shear stress in x direction. So this is actually giving the combination of stresses, the force coming from shear stresses. This is the force coming from pressure, force coming from shear stress, and this is the body force. So if this fluid is moving in a circle or anything, then there is some body force. So that is body force into per unit volume, mass per unit volume, rho fx. So you are getting mass into acceleration is equal to summation of all the forces. Fine. So this is the next direction. That is the Navier-Stokes equation. When I elaborate, and this is in y direction, this is in z direction. When I elaborate, because rho du dt is equal to this term, and this I have taken from John Anderson's book. You can go through it, very clearly written and very nicely explained. So rho du dt is actually total derivative, and total derivative is actually du dt, small du dt. In fluid dynamics, to emphasize that it is total derivative, we write capital D, capital T. Just to emphasize that it is total derivative, it is not partial derivative. And the relation between total derivative and partial derivative is this. So total derivative actually is consists of the unsteady part, which is dependent on time, and this uh, convective term, which is actually convective terms is because the fluid is coming from one place to another place. So when I replace this total derivative in terms of partial derivative, this equation takes a shape like this. Little derivative is there. I just derived it, and this is the final form in x direction, y direction, and z direction. And what is this is the Navier-Stokes equation. And what are these terms? The first term is the unsteady term. See that T is only available here. No, not other place. This next three terms are the convective terms. This is happening because of the convection. That is, fluid is going from one place to another place, and when it is going, by virtue it is going from one place to another place, it is carrying the fluid properties. So this is the convective terms. Then next one is pressure term. Then remaining thing, that part is diffusive terms. So this diffusive terms is happening because of viscosity. That is diffusion. Even if there is no convection, if I switch on a heater in the room and there is no fluid flow, you will still find that temperature is increasing in the room. That is because of diffusion. So that diffusion is happening because of molecular diffusion, which is actually depicted through viscosity. And these are the viscous terms or diffusion terms. And finally, there are some source terms. So this is the Navier-Stokes equation, which starts with unsteady terms, convective terms, pressure terms, diffusive terms, and source terms. And it gives a balance of momentum. So in my fluid dynamics, we got continuity equation, and now we got Navier-Stokes equation, that is momentum conservation equations. These are the relationship tau xx, how I relate these stresses with velocity gradient through Newton's law of viscosity. And this is the energy equation. So till now we talked about three momentum equation, one continuity equation. So I have four equations and I have four unknowns. The four unknowns are pressure and three component of velocities. In compressible flow, in hydrodynamics, like this course is on hydrodynamic design of marine vehicles, we have only these four equations and four unknowns: pressure and three component of velocities, and four equations: continuity and three momentum equation. But for sake of simplicity, I will say in actual fluid flow, if it is a compressible fluid flow, rho is also a variable. And in that case, we need to write the energy equation. Energy equation comes with density and temperature. So I add one more equation, two variables, density and temperature. And to close the equation set, we use the equation of state, that is PV is equal to nRT. That is the classical equation of ideal uh, fluid or ideal gas flow. PV is equal to nRT. So from there, now we got 6 equations and 6 unknowns. However, for hydrodynamics, these last 2 equations and last 2 unknowns are not relevant. Okay, so we got a closed set of equations. In incompressible flow, in terms of hydrodynamics, I'll speak. I'll say we have 4 equations and 4 unknowns. Pressure, 3 component of velocities, and 4 equations. Continuity equation and 3 momentum equation. So it is a closed set of equation, and we have enough number of equations to solve the remaining required unknowns. But only issue is that I go back to my earlier slide. Yes, look at this equation, Navier-Stokes equation. Okay, the first term is dou t rho u, and the second term is dou x rho u square, So it is a higher degree. U is coming as u square. Next term you see u and v are multiplied, so it is a non-linear equation. Okay, so complexity is that my Navier-Stokes equation is a non-linear equation. Now you see these diffusive terms. Diffusive term says that dou y into mu dou u dou y. That means dou to u dou y, 2 terms are there. Dou to u dou to y, dou to u dou to v dou y dou x. These terms are there. That is a higher order. So you see the Navier-Stokes equation is non-linear, higher order, and it is partial differential equation. Okay, that is nothing is total derivative, all are partial derivative, because u v w all are varying together simultaneously. Okay, so it is non-linear, higher order, partial differential equation, and it is coupled. That means u is coming in one equation, u is coming in second equation also. V is coming in one equation, V is coming in all other equations. So all the variables are appearing in all the equations. So it is not a, I have one equation for u, one equation for V, one equation for W. It is not like that. My all equations are mixed. So it is a non-linear, higher order, coupled, partial derivative equation, partial differential equation. Because of the complexities of this equation, till today, we could not get any closed form solution of these equations. From our knowledge of mathematics, we are unable to solve this equation using any partial derivative equations techniques or any partial. We don't get a solution of this equation. It does not mean that equation does not have a solution. Equation may have solution. Only thing, with our existing knowledge in 2022, we are unable, the human being, we are unable to find any closed form solution of this equation. So that's what is the limitation of theoretical fluid dynamics. I said that theoretical fluid dynamics has a limitation. Theoretical fluid dynamics has arrived to this equation, which describes the momentum conservation during the transport phenomena of fluid flow. Equation is available. Solution also may exist, but we are unable to find any solution for that. Our mathematics is not strong enough or not capable enough to get a solution of this equation. If we could solve this equation, we could just get a solution. A series of algebraic equation can be the solution of partial differential equation or differential equation, and that algebraic equation could give me the solution inside the entire fluid flow. But as of now, we don't have any solution for that. We may get some assumptions that for a very particular flow condition with some boundary condition, some flow condition, removing so many terms, ignoring so many things, making so many approximations, we can arrive to some solutions. In our fluid dynamics book, we will find many solutions like a pipe flow, Coutte flow, and all the flow conditions, many through two plates, flow through two plates, and all this. Many different conditions we use give so many approximations, so many assumptions, and with that limited condition, we get some closed form solutions of this equation. And that's why fluid dynamics book becomes so fat. Otherwise, this is the only equation, Navier-Stokes equation. And if we get a solution, we get everything. Unfortunately, we could not solve this equation. We don't have that solution. So that fluid flow problem solution is not available. That's why our book is becoming fat and fat. For different conditions, we try to make so many assumptions, try to simplify the equation, and try to get one solution for that particular set or that particular condition. And that's what is the subject of fluid dynamics. And that's why in the fluid dynamics book, you see so many different equations. But the origin of all this equation is this Navier-Stokes equation. And as I said, for my fluid flow problem, I need only continuity equation and Navier-Stokes equation for incompressible flow. And for compressible flow, of course, you add energy equation and equation of state. But in fluid dynamics book, there are so many conditions and so many ways these equations are solved because we don't have a general closed form solution of this. So this is the limitation, and this is the subject and domain of theoretical fluid dynamics. They do it in theoretical fluid dynamics. Now, what do we do in CFD, computational fluid dynamics? Now, because this theoretical fluid dynamics is unable to solve this equation, we don't have a closed form solution. We go for computational fluid dynamics. We solve it computationally. And as I said, these computational techniques to solve this partial differential equation started in 1900 or 1910. Precisely, I say that is the time people started giving some techniques how to solve this partial differential equation in an iterative way. It's not the exact solution of the partial differential equation, but in an iterative way, how this can be solved. So this techniques has been given. Okay, so this is and this is the job of CFD. So we have the partial differential equation, but we don't have the solution. So what I say that physical system we mathematically model. Physical system is that the conservation, that there is a transport phenomena, fluid is coming from one place to another place, it is going from one place to another place, and that physical system follows some laws of physics, which are the conservation laws. And now when I mathematically model, that has been already mathematically modeled, which is the job of theoretical fluid dynamics. And after modeling that mathematically, we have arrived to some governing equation. These governing equations are continuity equation and Navier-Stokes equation. And they are partial differential equation, non-linear. That's what I said, that is that they are higher degree, a higher order, non-linear, coupled partial differential equation. And we don't have a closed form solution for this. So we don't have a closed form solution. So we discretize it. We make some mesh in this domain. And in that mesh, we try to write the parameters and find out the difference between these two subsequent meshes. And from the difference, the rate, we get the gradient and we get the partial differentials. We write in form of a difference that can be a finite difference method, or we make a finite volume approach or finite element method to discretize the equations, flow equations. And for that, I need to do some pre-processing. I need to generate some grid. Then after pre-processing in that grid, we convert all these partial differential equation into quasi-linear algebraic equation. So there may be a series of algebraic equation because at every point I have defined the parameters. The density I have defined density 1, 2, 3, 4 at every point. velocity I defined v1, v2, v3 like that, and I arrive an algebraic equation which describes the relationship between this density and uh, velocities. And now we have the computer, so we can solve all this algebraic equation in the discrete grid points. And then once I get the discrete solution through some iterative method or some method, we get the solution and we post process and see the beautiful picture that all the solutions are available. So this is basically a CFD flow, and computational fluid dynamics does this job. So this is grid generation. Like if I have to do over a aerofoil section, see that this is the domain, I discretize the domain using a grid. And once we discretize the grid, this is the equation, the Navier-Stokes equation or continuity equation. I have written in a general form. That general form, earlier I have shown you, Navier-Stokes equation says that first is unsteady part, then the convective part, then the diffusive part, and then the source terms. So all these terms are written here. So this equation says that the unsteady generation of some parameters is balanced with its convective generation, or because of the convective transfer, diffusive transfer, and the source transfer. They are all in balance. So this is the transport equation, or this is the conservation law written in generalized form. And phi can be any parameter. It can be u, it can be v, it can be w, it can be p, it can be anything. So for any parameter in the fluid flow, this conservation law says that this parameter is conserved because it follows this particular pattern. Fortunately, all these equations, continuity equation and Navier-Stokes equation, energy equation, all falls under the same pattern. So we get a standard equation to deal with. So this is the transport equation, and we discretized it, and there are different computational methods. As I said, that finite difference method, finite volume method, finite element method, they all can be used for solving that governing equation. But in fluid dynamics, finite volume method is, in computational fluid dynamics, finite volume method is used so much that finite volume method has become almost synonymous to CFD. CFD means finite volume method. So I'll give some brief about finite volume method, what that finite volume method does. So it discretizes
Sir,
the domain.
that's sir.
Yes.
That's sir.
Yeah.
Sir, if you don't mind, actually hide that is coming now. Stop sharing and hide. Some participants are telling something you have written, it is not visible.
Oh,
Can you hide it, sir? If you don't
yeah,
mind, I am interrupting.
Yeah, I have.
Okay,
I have hidden. Sorry, I was thinking that it is visible for me only. I was also finding difficult.
No, sir. No, sir. Actually, from that, thank you, sir. You please continue.
And my cursor is visible to all of you, so that
Cursor is visible, sir. Cursor is visible.
Okay.
It's clearly visible, sir.
Yeah. So in finite volume method, what we do, see the same equation. Again, I am writing this. That is the unsteady term. This is the convective terms. This is the diffusive term. This is the source terms. So we discretize the domain in so many volumes, small volumes. That is the job of grid generation. So we generate the grid. So the domain is now split into so many small domains, and so many small cells. We call it cell. So to make a more accurate solution, the cell size of the cell has to be small. And to capture all the phenomena, the size of the cells to be small. So that's why it demands very high computational capacity, because if my domain is split into so many small cells, and that cells may run into millions. So for solving a particular problem, I may have to generate a mesh with so many, like 1 million cell, and it can be more. So in the domain, there will be 1 million cells, and that at the cell center, there will be all the variables stored. So if my variable is u velocity, that at 1 million places, u1, u2, u3, u4, all are stored. And in this numerical approach, we will establish some relationship between u1 to its neighboring node U2 to U3, U4, like that. That can be done through finite difference method also. In finite volume method, what we do, we take this transport equation, integrate it over the control volume. So here I have integrated it, and because of this integration, it finally leads to a difference equation which volume integral is now converted to surface integral using the Green's theorem, and finally it gives a relationship. It gives a relationship between the flux coming through my left face, flux going out through my right face, flux coming in through the top face, flux coming in through the bottom face, the north face, south face, like that. So all the six phases. So when I integrate the transport equation inside the control volume, it basically gives me a balance equation saying that the flux coming through my north side plus south side plus east side plus west side plus top side plus south the bottom side is in balance. And that is the essence of finite volume method, and this is the derivation. And you can use Malala Shekhar Verstig and Malala Shekhar's book. I have taken from Verstig and Malala Shekhar's book on finite volume approach. The earlier part I have taken from John Anderson's book. He has described the fluid flow equations very well, whereas finite volume method is explained better in Malala Verstig and Malala Shekhar's book. I have taken from there, and all these equations are derived there. So it finally states me that the balance between the flux coming from all the phases are established. And once I get that equations, so for every cell, I can write the equation U1 in terms of U2 plus the boundary condition, like UN velocity at nth node can be related with n plus 1th node, n plus 2th node, n minus 1, n minus 2 node, and the boundary conditions. And after I store all these equations, see, I have stored all these all the variables at the cell center. But for writing for writing or establishing the gradients, I need to know the value at the cell face also. I have stored the values at cell center, but at the cell face, what is the value I need to know? So we use some discretization scheme to relate the values from cell center to cell face. And this discretization scheme can be forward difference, backward difference, central difference, appoint scheme, compound scheme, like that. Depending on the flow in your CFD solver, you can choose this discretization scheme. These are basically the schemes to relate the values from the cell center to cell face. So forward difference says that dou u dou x will be ui plus 1j minus uij. This is the forward difference you all know from finite difference by del x. Backward difference, use this backward difference technique. Central difference is using these things. In CFD, we use appoint scheme also, because see, this forward difference, backward difference, central difference are the direction independent. It does not depend on the direction. Flow may be coming from left to right or right to left, but this forward difference and all these things are same. So if I have to take the value from one place to another, from here to here, the forward difference or backward difference all will be independent of the flow direction. But if my flow is happening from left to right, I see the influence of a point at I minus 1 will be more on ij, on this point ij, than I plus 1j, because I plus 1j is at the downstream. So influence of a downstream point is less than the upstream point. So if I have to consider the direction, the upstream point has to have a better influence. So to do that, we can use pure appoint scheme. You can see this picture. Pure appoint scheme says that whatever value is available at I minus 1 node is directly used at this phase. That's pure appoint. We can use linear appoint. that we take two nodes from upstream and do a linear equation and take the value here at phase. We can take a quadratic scheme, two at upstream and one at downstream, and do a curve fitting and take the value at the phase. So these are the appoint schemes. One can be pure appoint, linear appoint, and quadratic appoint. It can be forward difference, backward difference, central difference also. Mostly central difference are used. So these are these discretization schemes, and it can be hybrid also. Sometimes that for diffusive component, diffusion is independent of flow direction. So for diffusive component, we take central difference. For convective component, we take appoint schemes. Okay, so this is the way we transfer the values from phase to from the center to phase to write the equation. And the discretization scheme basically gives me discretized, or the numerical scheme basically gives me a series of algebraic equation which relates the parameters, values u, v, w, and their relationship with the neighboring values. And once I get that equation, we can solve it using some series of algebraic equation, and in a computer I can solve it. As a computer, you will be able to solve these things. This approach is done in a segregated way or coupled way. Segregated way means I solve one for U governing equation, then update my flow field, then solve for V governing equation, again update my flow field. First, I give an initial guess and then solve for U, solve for V, solve for W, solve for P. I keep on doing it progressively. And in a coupled approach, I solve it together. U, V, W, and P, solve it together. So nowadays, because the RAM and all are improving in computers, the coupled approach is more used. And if you have some RAM limitation, you can go for segregated approach. Otherwise, coupled approach is now the norm everywhere. Mostly it is used with a coupled analysis. So with this, we have discussed that how the fluid flow is described and how the computational, how the fluid flow is described from the physics, what are the governing laws, and from that laws, how do I write the governing equation, and this equation forms the theoretical fluid dynamics. Unfortunately, we don't have a solution of this equation, closed form solution of this equation, so we try to solve it computationally. And to do it computationally, we use finite difference method, finite volume method, or finite element method. Mostly in fluid dynamics, finite volume method is used, and almost CFD has become synonymous with finite volume method. So I have series of differential equation, 4 differential equation. We discretize it in the entire domain. There may be millions of cells in the domain, and in every million cells, we write this equation in form of algebraic equation. That is the part of numerical scheme or computational scheme. And once we convert the differential equation in the form of so many algebraic equation, that may be millions of equation, but in a computer it can be solved. And that is the essence of computational fluid dynamics. So fine, this is computational fluid dynamics. Now I will say this is fine, but most of our engineering problems are turbulent flow. And the turbulent flow scales are so small that time scale and length scale. That means my eddy vortices are so small in turbulent flow that my mesh size requires to be very, very, very small. And time step also to be very small, because these are happening in very small time scale. And if my domain is very big, for a ship, I have to consider a very large volume. So I need to have so many cells and so many time steps, which is a challenge for any modern day computer. So that's why for turbulent flow, solving turbulent flow, it becomes very difficult, because computers are not sufficient to solve such equations in such a fine resolution. Okay? So, but our engineering problems are mostly turbulent. So the approach what I told it till now, if I solve it straight away, without considering any turbulent laminar flow, it is called direct numerical simulation. That means I solve the flow as it is. It may be turbulent flow. It will resolve everything and it will give me solution for turbulent flow. That is direct numerical simulation. But that demands very high resolution of mesh, very high resolution of time step, that means very fine time step. So it demands very high computational power, which is impractical for many of industrial problem today. So for turbulent flow, we cannot solve the flow straight away. We do some modeling, and that modeling actually initially was given by Reynolds average Navier-Stokes equation. Reynolds has given a scheme that instead of solving turbulent flow as it is, we solve some time average solutions. Like if you see, this blue line is the this scale is this is time, and this is any parameter u, v, w, or p, anything. See, blue line is the fluctuating line, which is a turbulent fluctuation, and red line is the time average thing of that same. So in Reynolds average Navier-Stokes equation, principle is that the assumption is that the turbulent fluctuations are happening. Okay, this blue line, there are many fluctuating components. But as an engineer, we are not bothered, or we may not require to know all these fluctuations. Because if a pump is giving some water, say 100 liter per minute, that is the answer. At some stage it is 100.1 or 99.9. We are not concerned about that small botherations, small fluctuations. So that blue line, actually we know we don't need. A red line is good enough for our solution. Okay, so Reynolds average Navier-Stokes equation says that we solve it using time average it, and
Dear participants, sir, I think within 1 or 2 minutes he will join. So at the end of the session, one Google form will be given. In this small feedback and the organization of our FDP, as well as it acts as the attendance. So as you know, 80% attendance is mandatory to give the certificate. So you kindly fill this and please cooperate with us. And we are soon, all the dignitaries are very, very good, as you have seen from the timetable. And the first session also, it started in a very well manner. Okay. So definitely offline also, I wish to see you everybody. Sir will join soon. I think some calling bell, some disturbance, it came. He will join. That's why I'm talking in the meanwhile. So you please, all the participants should stay online. So somebody are quitting. 50 participants are there, and it is late hours only. All of you can stay, but some only 34 it is visible in the attendance.
Shastri sir.
Yeah, tell me.
Good evening, sir. Sir, I have a query regarding offline.
Emma?
Offline session, sir. It's like on
1
7.
minute. Das sir call చేస్తున్నారు, నేను మాట్లాడతాను మళ్ళీ.
Okay, sir.
You are from where?
I'm from Chennai campus.
Sir, Das sir has joined, sir.
Thank you, sir. Thank you. So you take my number 94901079949. You call me.
Das sir,
I will
your
give you the
voice is
time.
not audible, sir.
sorry, my laptop battery got discharged actually, so it automatically got shut down.
Okay, sir, fine, sir.
I just put
Okay,
it
sir.
in.
No problem, sir. No problem. So my phone number is given in the chat box. Anybody wish to WhatsApp me or talk, please. Dr. Rakesh, you are from where?
From Chennai, sir.
Okay, okay. Sir, you please continue.
I have almost come towards the end only. I was saying for turbulent flow. Yeah.
Sir, it's no issue, sir. You can close at any time. It's given like that, but as per your convenience, you can take.
So nice of you, but it will become heavy for me if I was sitting in the audience. More than 1 hour would have been difficult.
No, no, no,
Anyway,
sir. You can conclude, sir. You can conclude. We understand. You are coming. It's more than for us.
yeah. So as I was saying that as an turbulent flow, there is a issue that it is problem to get such a fine resolution in time and space domain. So as an engineer, we say that this red line, that is time average solution, is good enough for us. So we need not take these fluctuating components of turbulence. So that's what Reynolds has given a concept. How do we solve that time averaged parameters? So if you see these two pictures, the left side is that instantaneous view of a jet, and time averaged view of this will be like this, right side. So if this is a real flow, real turbulent flow, instead of getting this solution, we will be arriving to this solution. But as an engineer, this may be good enough. In many places, this is actually a good solution. We look for this solution only. So that is the concept of time averaging. And this is, I wrote in the last, Reynolds average Navier-Stokes equation. So in this Reynolds average Navier-Stokes equation, what we do, we segregate the parameters, all velocities, everything in a time averaged part plus the fluctuating component. If you see this, I wrote that phi is equal to phi bar, which is time average, plus phi dash, that is fluctuating component. And we intend to solve only phi bar, not phi dash, because that is fluctuation, that is very small, and we can ignore it. Okay, so in Navier-Stokes, Reynolds average Navier-Stokes equation, we solve the time averaged part, and that fluctuating component we model, we mathematically model. The effect of fluctuating component we mathematically model, and that mathematical model is called the turbulence model. So you must have heard in CFD, in fluid dynamics, turbulence model, turbulence model. Turbulence model is that this fluctuating component of turbulence, we don't solve as it is, we model it. And that modeling is the turbulence model. Okay. So what I said that the entire Navier-Stokes equation as it is, if I solve using CFD, this is called direct numerical simulation. The first one. I don't do any modeling. I solve it, but it demands a very fine mesh, very small size of the mesh, and time steps. If I have a powerful computer to handle that, we can go for direct numerical simulation. It will take more time for computer, more computational resource, more storage space, but it will give me a actual direct numerical solution, actual solution of turbulent flow. If I don't have that kind of resource, computational resource and time, and I don't need to know that kind of detail, we can go for modeling. And this modeling is that Reynolds average Navier-Stokes equation, where the fluctuating components are modeled using turbulence model, and time average components are solved out. This is Reynolds average Navier-Stokes equation. This is actually the standard in industry. Today, if you see in industry solution, Reynolds average Navier-Stokes equation is being followed or practiced in most of the industries, in most of the turbulent flow. Little improved in between, there is one thing called large eddy simulation. Large eddy simulation says that the larger eddies of the turbulence, larger eddies of the turbulent flow are simulated as it is. They are simulated. They are not modeled. But the smaller eddies of the turbulence are modeled. That means my grid size is not that small, but it is small enough to capture the larger eddies of the turbulence. And even the smaller size, that subgrid size eddies, they are modeled. So it is a compromise. It is something middle between DNS and RAMS is large eddy simulation. So for turbulent flow, there are three different approach. We can say Reynolds average Navier-Stokes equation, the large eddy simulation, and direct numerical simulation. And there is another approach called detached eddy simulation. The detached eddies are simulated, but the eddies which are attached to the boundary layer are modeled. That is also there. So these are the turbulent flow approaches for turbulent flow, and I think I will be giving a offline lecture on turbulent flow. So that's why I will not get into the remaining part of the presentation, which deals with turbulent flow. In fact, that turbulent flow, I'll give a detailed presentation when I come there in the same program. And with this, I will come to this summary of this talk today. So what we have discussed that the fluid flow problem is when fluid is flowing, it is actually a transport phenomenon, and there are physical laws which are conservation of momentum, conservation of mass, and conservation of energy. So physics gives us the conservation laws, and these conservation laws can be written in terms of governing equation. That is the mathematical modeling. So mathematical modeling of these physical laws are also done. That is the part of theoretical fluid dynamics, and theoreticians are good enough to derive this governing equation, which are continuity equation, Navier-Stokes equation, energy equation of state, and all. And with these equations, we have 6 unknowns, 3 components of velocities, pressure, uh, density, and temperature. And we have 6 equations also. One continuity, 3 Navier-Stokes equation, energy equation, and equation of state. So there are 6 variables, 6 equations. We have a closed set of equations, and entire fluid flow problem is defined. That is the theoretical definition of the fluid flow equation. The problem becomes, unfortunately, we don't have any closed form solution of these partial differential equations. They are very complex partial differential equation, higher order, non-linear, coupled partial differential equation. Until today, we have not got any closed form solution for that. So because we have not got any closed form solution, we need to solve them computationally or numerically. So there are numerical techniques to transform this partial differential equation into series of algebraic equation. And to do that, to convert it to series of algebraic equation, we have to discretize the domain. We have to make small control volumes in the entire domain. And at every point, we define the variables, or we mark the variables as different cell points, U1, U2, U3, P1, P2, P3, like that. And after generating the grid, discretization is done. We can convert this partial differential equation into a series of algebraic equation. If there are million cells, there will be so many millions of algebraic equation. But a computer can solve this equation, because computer has. That's why I said that initially when these techniques were developed in 1910 or so, we did not have computer. So techniques were there, but still we could not do anything with these techniques. So that's why numerical science or computational science was not popular at the beginning of 20th century. But towards the end of 20th century, it has become very popular because computer has come in, and there was some tools which could solve this numerical schemes. So that's how we solve the fluid dynamics equation in form of computational fluid dynamics. But there are some additional problems for turbulent flow, because turbulent flow demands very high resolution in time scale as well as in space. So we derive Reynolds average Navier-Stokes equation, which models the fluctuating component of turbulence parameter and solves the time average components as it is. And to do that, we need to do some turbulence modeling to model the time average, to model the fluctuating component of turbulence. And once this modeling is done, so that modeling is again approximate, because it is modeling, it is not the actual solution. So a turbulent flow solution is as good as the turbulence model is. So if you have using a good model, you get a good answer. If the turbulence model is bad, the answer will be bad. So that is the lacuna or the difficulty for turbulent flow. But as of now in industry, we live with RAMs, and for any turbulent flow, we go ahead with RAMs with appropriate turbulence modeling. And this is, in summary, essentially we do in computational fluid dynamics in CFD. I have not derived this equation from partial differential equation to algebraic equation. I think that is the part only missing here in this lecture. But for an introductory course, I think that is not required. I do it as a classroom lecture when I teach the semester course for MTech students and all. Anybody interested, we can still discuss. We can still carry on and we can further discuss on this derivation of these equations. So with this, I conclude. Thank you very much. I am ready to take any questions. Any questions you can ask.
My dear participants, you please ask. If you ask questions, we feel you listened. If you do not ask, you just simply muted and sitting. I request few participants to ask questions, including Narsimha and Sairam.
Good evening, sir. Sir, am I audible to you?
Yes, you are audible. Please.
Yeah, good evening, sir. My name is Rakesh Kumar. I am from Chennai, sir. So I have a couple of queries regarding CFP since I am new to this field. Just I want to explore this field so that I am attending this FTP program. The first thing is, sir, is there any general grid volume shape we take for these problem solving? Like there are many types of volume shapes like hexagonal, tetragonal, octagonal. So which type of volume shape do we generally prefer for grid generation?
Yes, there are many different shapes you can take for volumes, control volumes of the cells. In three-dimensional field, it is, as you rightly said, it may be hexahedral or maybe tetrahedral. These are the most common forms used. In 2D, it generally eventually boils down to quadrilaterals and triangles. So in 3D, it is tetrahedral or hexahedral. And recently, polyhedrals are also coming. I will say the preference between tetrahedral and hexahedral is that hexahedral is easy for the solver. For any solver, any better, any solver, hexahedral is easy. And hexahedral, one advantage of hexahedral is that it can be stored in structural form. It can be stored in a structured grid. That means structured grid means its connectivity is automatic. You just draw a series of x direction and series of y direction curves, means two orthogonal set of curves, and you generate a grid, and your connectivity is automatic. Means it's starting from I equal to 1 to n, j equal to say 1 to m, and at at any ith location, jth location, you know where you are. The connectivity is automatic, and the transfer is gradual. So we expect better result, and it is easy for the solver. For solver, your storing data is easy. Computing the gradients are easy for hexahedral mesh. So a better quality mesh can be generated using hexahedral, no doubt about it. Okay. Now, difficulty is that, and it can be stored in structured way. It can be stored in unstructured manner also, but tetrahedral cannot be stored in structured. It's not possible because tetrahedral, how the connectivity, where is your first tetrahedral and where is the second tetrahedral, how you have connected, that connectivity is not explicit. You have to mention that how you have connected. And tetrahedral, these changes are also not gradual. The gradients are changing, not gradually changing. So tetrahedrals are difficult for the solver to handle. Now, thing is that for any complicated geometry, imagine if you have a very complex turbine blade and there you want to generate hexahedral mesh, it is extremely difficult to generate hexahedral mesh. So practically for difficult, complex geometries, it is very difficult to generate hexahedral mesh. So that way, hexahedral is sometimes it is impossible to generate hexahedral mesh.
Oh.
So your option is that you have to go for tetrahedral. But if you give me a choice between hexahedral and tetrahedral, from solver point of view, for writing the code and all, hexahedral is much easy for the solver, much expected to give much accurate result. And earlier days, actually, solvers were not capable to handle tetrahedral mesh. So, but nowadays, anyway, solvers have improved. Many good solvers have come, and some solvers are so good that the difference of result in hexahedral and tetrahedral mesh is almost minimal. So, results are comparably good. So,
Okay.
that way, if you have a very good solver, you may not mind. You can go ahead with tetrahedral mesh. But if your solver is not very good, if you have a bit weak solver, I prefer you go for hexahedral mesh. And your geometry is very complex. You don't have any choice. You have to go for mesh.
Okay, sir. Sir, my
Is it
next
clear? Have I
yes,
answered?
yes, sir. Thank you, sir. And my next question is, sir, like the field variables which we are finding in the physical equation, in mathematical equations, using algebraic conversion into algebraic equations.
Hmm.
The field equations are we like finding out at the center of that grid mesh,
Hmm.
be it 2D or 3D, and we are extracting or extrapolating that center field variables to the surface
Yes.
to use that convection heat flux at the left, right, or
Hmm.
top, bottom,
Hmm.
right, sir?
Yes. Yes. See, normally these fluxes are stored at the cell center. As a normal convention, you may write at the cell face values also. Normally, it is not written. All the cell center values are stored in your matrix.
Yes.
Okay. But when you are writing that difference equation between U1 and U2, relationship between U1 and U2, there will be some differences. That is the flux going from one cell to another cell. That depends on the value at the cell face. At what rate it is going from cell 1 to cell 2 depends on the value what is happening at the cell face. So temporarily you want the value at the cell face also. So you know the value at cell center U1 as well as U2. From there, basically we interpolate, get the value at the cell face. This is an interpolation technique basically.
Using a central difference method or forward
You
difference,
may,
backward difference.
you may use forward difference, you may use backward difference, you may use central difference as well as some point scheme. Because sometimes if it is a very convection dominated, the convection is very high and a upstream upstream node value may have a huge influence on that cell face instead of that downstream value. Okay.
Okay, sir. Thank you very much, sir. Thank you.
Tota Navin is from Indian Maritime University, Chennai, sir. Other participants? Any participants, please?
I mean, I used to teach in Indian Maritime University at Visakhapatnam.
Oh, okay. Actually, I recently joined, sir, 1 year back.
Few
And I
few years semester course I have taught them CFD for few semesters. Now somehow I got busy with my laboratory work. I am unable to spend time there.
okay, sir.
So thank you very much, sir. I think some in chat box somebody given, sir. Sir, some of the reputed journals are asking to validate CFD results with physical experiments, even for academic level publications. So, what are the wind tunnel or water channels available in our country for academic research? Nikhil Chaitanya has given.
Yeah, see, wind tunnels are available in most of the academic institutes. You go to mechanical engineering department or aerospace engineering department in most of the academic institute, including NITs and IITs, you will have wind tunnel. As far as water channels are concerned, IISc had one cavitation tunnel. IISc Bangalore had one cavitation tunnel. I am little apprehensive if it is still working or not. NSTL has one cavitation tunnel, and IIT Madras Marine Department, that Naval Architecture and Ocean Engineering Department has a towing tank. So has IIT Kharagpur. Ocean Engineering and Naval Architecture Department at IIT Kharagpur as well as IIT Madras, they have a towing tank. And cavitation tunnel, we have cavitation tunnel at NSTL as well as towing tank we have. We have one sea keeping and maneuvering machine that is actually unique in Asia. In Asia only we have. No, sorry. In Korea, 2 or 3 are there. In India, we have only one sea keeping and maneuvering machine. You may not require sea keeping and maneuvering machine, but wind tunnel you will be getting in most of the academic institutes.
Okay, sir. Thank you very much. I hope other participants do not have any question. Sir, we hope we will see you in the offline session also. Thank you for sharing your very valuable knowledge to us, sir. On behalf of the Department of Mechanical Engineer and my co-coordinator and student coordinators and all the participants, we are very much thankful to you, sir. Santosh.
Thank
Sir,
you, sir.
Sir, thanks a lot, sir. It was indeed a great pleasure to attend your lecture, sir. Actually, you have given a clear view about the introduction to CFD, sir. It was really helpful for us.
I request all the participants to fill the Google form. It is also in the WhatsApp group. It is given. From tomorrow onwards, I request all the 50 participants to be in the online because it is from evening 7 to 9 only. Thank you very much, sir. It is, you can see the YouTube link also because in the YouTube also I have shared. So the total will be coming in the YouTube, sir. You can share it with your friends also.
Thank you,
sir. Namaste.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you very much, sir.
I'll sign off.
Yeah, thank you, sir. I am also signing off.
Thank you, sir.
Thank you all the participants. Tomorrow we hope we will meet together. Okay, thank you.